What's going on, everyone? Welcome back to my YouTube channel. It's Max, and this is the fifth part in our video series about how to make your own crypto app. Last video, we talked about the Diffie-Hellman key exchange and how that works. And just like when we started programming the Enigma machine, we did that in two parts. We did one part where we actually coded up all the encryption logic and things like that. And then the second part, we did the user interface. And the next two videos are going to be pretty similar with the Diffie-Hellman key exchange. Today, we're going to start talking about some of the implementation details to just do the Diffie-Hellman key exchange and the modular arithmetic. And then in the next video, which will probably be the last video in the series, we're going to just finish up the application with the GUI for the key exchange itself. Here are the four main things I want to cover in this video today. The first is just how to do modular arithmetic in C#, and this is going to be pretty straightforward. The second is how to do modular exponentiation. And the reason these are two separate items is because the exponentiations we're going to be doing are going to result in very, very big numbers. So we're going to do stuff like some number raised to the power of millions. And those numbers are going to be so big, they're going to overflow the data types in C#. So we needed a special way to do these without, with preventing the overflow from happening. The third item is to get a list of big prime numbers we can use for the modulus and the Diffie-Hellman key exchange. And then the last thing is some more subtle details about preventing overflow when we do these big exponentiations. So here's an example of how to do modular arithmetic in C#. So suppose you wanted to compute some equation like we have right here in the comment, that is y equals g to the x mod p. All you have to do is, to do the exponentiation, you can just say math.pow base comma exponent, so g comma x. And then to do the mod operator, you use this percent symbol. So this line right here is just implementing this equation in the comment. So let's look at what happens when we run this. Okay, so according to C#, the result is 0. So 0 is equal to 57 to the, it looks like there's 7 ones here, so 57 to some power over a million mod this thing. So the first thing is this right? And it could be, right? Like 57 to the power of 1,111,111 mod this thing, it could be 0 if this number perfectly divides this. However, I know for a fact it doesn't because I specifically chose this p to be a prime. So this answer is incorrect. And the reason it's incorrect is because C# is, this is what C# will do when it encounters an int overflow. Because 57 to the power of something over a million goes over the range of uint, which is the biggest number a uint can be is 2 to the 32 minus 1. And actually, let's just see what that is really quick. Where's the C# interactive window? We can just test it really quick. So let's say uint y2 is equal to math.pow 2 to the 32 minus 1. So let's see if this will, oh, this needs to, when it does math.pow, it returns double, so I have to cast it to a unsigned int. Okay, let's see if this actually can compute. I'm not sure if this will overflow, just the math.pow by itself. Okay, looks like it didn't. Let's see what we get. Yeah, so I think this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So uint 32, we can go from 0 to about a little over 4 billion. Okay. So yeah, so when we ran this program, we got 0, and that was because of an int overflow. And one small thing aside, not having to do with modular arithmetic, is this is kind of an annoying thing about C#, how this didn't actually crash, but it just gave you the wrong answer. And usually in programming or software development, that's the last thing you want to happen. You never want to have a program do something wrong and not tell you. So if you're ever doing something like this and you want to make sure your program catches an int overflow in C#, you can add this checked command or checked function. And then this should throw the exception for the overflow. Yeah, there we go. Arithmetic operation resulted in int overflow. Now the question is, well, how are we going to compute something like this? Like 57 to the power of 1.1 million mod this thing. And there's two answers to that. One is in C# and in most programming languages, they do have data types for arbitrarily large ints. So you can have, integers that aren't really constrained by any sort of like 2 to the power of something. You can have integers that are hundreds or thousands of digits long, and it'll just do arithmetic on them fine. The other way is to take advantage of some properties of modular arithmetic to, instead of computing some giant exponent like this, you can compute a series of much smaller multiplications that'll you'll still end up at the same result as the big exponent. So let's go over what that property is and how we can use it. So suppose we have an equation of this form like we were trying to compute just now. Y is equal to a to the b mod p. So one way, if we were to expand this exponent out, we know it's just a series of multiplications, right? We know that this is just y equals a times a times a dot 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 times a mod p, where there are b many of these. So the property we can take advantage of to compute this without overflowing is the fact that we can compute each one of these multiplications individually mod p and then use the result with the subsequent multiplication. So what I mean by that is, let's do an example with just the multiplication of 3 numbers. So suppose we have y equals x times y times z mod p. Instead of having to compute x times y times z before doing the mod p operation, we can actually compute, I probably shouldn't call this y, let's call it w since we already have a y. Instead, we can compute x times w mod p, and then take the result of this and multiply that by z, and then compute that result mod p. And so the way we can take advantage of this is that now, instead of having to compute a to the power of b, where b can be some huge number like in the millions, and where this is likely just going to overflow our data type, all we have to do is compute things that are on the order of just a squared, or a times a, or a times some number that's the result of another multiplication. And that result anyway is going to be constrained by p because of the mod operator. So the biggest number we're going to have at any given point is just going to be, we're going to have to be able to compute a times, at most, p minus 1. And that multiplication is going to be way, way smaller than just directly computing this exponent. Now that we're aware of this property, let's code up an implementation of this exponentiation that takes advantage of this to only compute smaller intermediate multiplications, but end up computing the entire exponent in the process. So let's make a new method. Say public static, we'll return a uint, and we'll just call this modular exponentiation. So we'll say mod exponent. And what we're going to try and compute is the following. We're going to compute y equals a to the power of b mod p, just like our example. So we're going to have a uint a, uint b, and a uint p. So we're going to have some result y, and right now that'll also be a uint, and that's just going to start at 1. And what we need to do is basically multiply y, whatever y currently is, times a mod p, and do that b times. So we're going to say for int n equals 0 while n is less than b, n plus plus, and we'll say y is assigned y times a mod p, and then return y. And now all we're doing is just having to compute something like y times a mod p and just do that over and over and over again. And every value of y we get is always going to be constrained by p. So this shouldn't ever overflow as long as this smaller term doesn't overflow. So let's give that a try now. So just like we made it some variable y1, we'll make a y2 and we'll do the exact same computation, but we'll use this new function we just made instead of directly computing it in C#. So we'll have mod exponent, and in this case our a is our g xp, and this will be y2. And let's just do another print line, and we'll just see what this answer gives now. And oh, we should also remove the check so it doesn't throw the overflow exception. Signed. Okay, let's see what we get. Okay, so where in it overflowed, it returns 0, and now it's saying the result of this is this number. And let's see, this is how many numbers are here? 1, 2, 3, 4, 5, 6, 7, 8. So 11,001,811. Okay, so now the question is this right? And I'd say the best way to check is let's check this on Wolfram Alpha and just see if they get the same result as well. Okay, so this is what we had. And yeah, Wolfram Alpha returns the 11,001,811, and that's the same thing what we got. So I think this is a good sign that builds confidence that we that this is coded properly. Cool. So that deals with these first two items. Item 3 is this prime list. So we need a list of very large primes for our program to use to use as the modulus for all of our modular arithmetic for the key exchange. So to get that, I found this website. Actually, I forget what UTM is. I think this is just some university. And they actually have all these pretty cool files, actually. This is the first million primes from 2 to this 15 million. And if you guys didn't already notice, actually, no, I didn't use this prime. I used the first prime in the second million set for this P. And that's how I knew we had a prime number. So when it returned 0, I knew that was wrong. So we can just download any one of these lists and use that as our modulus for all the key exchanges we do. So let's just pick one. Maybe we'll use the I guess we can use any. Let's use the 10th million. How about that? The 10th million set of primes that goes from about 160 million to 179. So we'll just save this, the zip file, and then I just have that in my downloads. Cool. Okay, so that one's pretty simple. We just downloaded a big list of primes, and actually let's open them and see what it looks like really quick. Just gonna open my downloads. Okay, it's just a big text file. And we get something like this. Yeah, this is it's a really big file. Okay. So maybe we use this whole thing, maybe we don't. And it looks like we're gonna need a way to parse it because there's this kind of weird space up here, this like weird indent, these spaces. And we'll probably worry about that in the user interface design video for the second tab about how we're actually going to deal with this file. But for now, we have a ton of primes we can use as a modulus for a secure key exchange. Sorry about that. I think there's a dog having fun behind me. Okay. So item 4, overflow prevention. Yeah. So this is just one more detail about preventing the overflow. So, and actually, so we made this modular arithmetic or modular exponentiation function right here. And the reason why that works is because instead of computing some huge exponent like a to the b, the smallest thing we have to compute is y times a mod p. And so that multiplication is going to be much smaller than the original exponent. So let me just get both of these on the screen really quick. So all we have to make sure is that y times a can never be bigger than 2 to the 32 minus 1. And since we know that the result of y is constrained by p, specifically that y can never be bigger than p minus 1, we can come up with the following equation that must always be satisfied. So we can say that, y times a has to be less than 2 to the 32, 2 to the 32 minus 1 to prevent overflow. And we know y can never be greater than p minus 1 because of the modular arithmetic. So we can have p minus 1 times a, that must be less than 2 to the 32 minus 1. And then assuming we pick p first, we can just solve this equation for a and replace this with an equal sign. So if we did that, we know that if we have some p already, we know that a must be, I guess I should say a is less than, actually let's keep the inequality. If we just solve for a must be less than 2 to the 32 minus 1 divided by p minus 1. And while you probably won't cause an overflow because of this fact, it will just be a nice thing to build into our application to say, like, there's no reason the user needs to select this g, this base, and this this prime. They will be selecting the exponent because the exponent, remember, will be their private key. But we can have the program automatically generate these for Alice and Bob or whatever two people are using the app. So we just want to make sure that we'll have the program generate the prime first and then generate the base to satisfy this constraint so we never overflow in this method right here. And that's the last thing I wanted to cover in this video. So thank you all for watching, and next video will be the final video in the series about how to make the encryption application. And that video, we're going to take all the things we did today and use them to implement the Diffie-Hellman key exchange in that second tab, and then build out the rest of the interface. So again, thank you all for watching and following this series, and I hope to see you on the last video. Bye.